Hello everyone. Okay, the topic for today is equilibrium. And we're going to look at objects which are in equilibrium. However, before we get to any of that, I thought it'd be really useful to do just a little bit of a recap from where we've come from, because we've considered objects that are not in equilibrium often. They do have a resultant force. They are accelerating. That acceleration is often constant, so we use suvat. And so we're going to need all of these ideas really to make sense of what we're about to look at. So just very quickly, quick recap. The diagram that you've got in front of you, object down the slope, it is accelerating. We have a force down the slope. You know that there is also a normal contact force, sometimes called a reaction force. So we've got a force down the slope that's parallel to the slope. We've got the normal contact force that's perpendicular to the slope. Those two are at right angles to each other, so they are completely independent of each other. But we've also got weight, and notice each of these three vectors are originating from the centre of mass of the object, as they should do. Now, I can resolve weight parallel and perpendicular to the slope. So if I resolve weight perpendicular to the slope, there is a component of weight, which looks like the adjacent side of a triangle, and there is a component of the force down the slope which looks like the opposite side of the triangle. So I think this is W cos theta because it's the adjacent side of the triangle. So what have I done there? I've done something called resolving perpendicular to the slope. And what I'm going to say is that that component of weight, W cos theta, is equal to the normal contact force. And that is true because the object is neither sinking through the ramp nor is it floating away from the ramp. But I could also resolve parallel to the slope. And for that, I need to know this component of weight. That looks like it's the opposite side of the triangle, W sine theta. So I'm going to say that W sine theta is equal to the force down the slope. Okay, so that is just a reminder, okay, of taking components of forces and relating them to other forces for objects that are moving up and down slopes. On the PowerPoint slide, you've got then a worked example of how to kind of identify these components, how to do a calculation, and then a couple of quite detailed worked examples, okay, involving resolving suvat, etc. I'd really recommend that you have a good look at that and work through those questions and check that you're really happy with those. Okay. However, today is all about things that are in equilibrium. In other words, where we've got zero resultant force, where objects are not accelerating. And I want to take you through just some thought processes for how to work through examples such as this. Okay. On the PowerPoint slide on your left, then, you've got an object in blue, and there are three forces acting on it. Two tension forces, and you've got weight. We want to know, is that object in equilibrium or not? And so the way that we might do that is we place the three vectors tip to tail. So there's the first tension vector, and there's the second tension vector, and there is the weight tension vector. Okay, now the important thing here is that each of those vectors are drawn to scale. Assuming that they are, I have now formed what we call a closed triangle. In other words, all the vectors line up tip to tail, and so I can deduce from that there is no resultant force acting on that object, and therefore that object is in equilibrium. And that's a graphical way that we can deduce whether things are or are not in equilibrium. Okay, now just to show you what it would look like for it not to be in equilibrium, let's imagine that when I drew the weight vector to scale, it looks like that. That is not a closed triangle, and therefore you could not deduce that that object is in equilibrium. Okay, the second way of thinking about things then. If we draw the pair of forces tip to tail. Now, pairs of forces generally mean the same type of force. So in this case, the two tensions, I've drawn those tip to tail. Okay, what we know is that the resultant of those must equal the weight. And if that is true, then that object is in equilibrium. Okay, so this would be a good method to follow as well, kind of graphically by drawing this out. Okay, but the interpretation you're going to use the most, I think, is the third one, which is kind of resolving your vectors. So if we just draw the equilibrium line to reference our two tension vectors against. Okay, one thing to note is that both of these are at the same angle, theta. More on that in a moment. Okay, so we've got tension and we've got tension. Okay, each tension has a vertical and it's got a horizontal component to it. Okay, so we've got T sine theta here because it's opposite to the angle, and we've got T cos theta there because it is adjacent to the angle. Okay, and similarly, I can split that tension also into my horizontal and vertical components. Okay, now I've got weight acting, and weight acts vertically. So let's consider life from a vertical perspective first of all then. So I've got T sine theta from the left-hand tension, and I've got T sine theta from the right-hand tension. They are both acting vertically, so if I add them together, then that ought to be equal to the weight. And similarly, I can consider life from a horizontal perspective, and I can say that horizontally, T cos theta and T cos theta are equal to each other. Okay, and I'm not going to reference weight here at all because horizontally, there is no component of weight. Weight only acts vertically and therefore is not relevant when we're considering things from a horizontal perspective. Okay, so we've got kind of a graphical tip to tail kind of model for working out whether things are in equilibrium, the closed triangle idea, and then we've also got the resolving vector idea as well. Okay, couple of examples then for you to look at. Apologies about all the scribblings. I've drawn on here an object with the normal contact force, friction and weight. And let's get rid of all these scribblings, shall I? That's better. Then you can actually see what's going on. I have drawn now each of those three vectors tip to tail down there. And I have formed a closed triangle. It happens to be a right angled triangle, but that's not the important thing. It's a closed triangle, and therefore I can deduce that that object is at equilibrium. Okay, similarly here, the cable car example. We've got two tension vectors and we've got the weight vector. And I've put all three of those tip to tail, and I've circled them in purple. I have not formed a right angled triangle, but that isn't important. What is important is, again, I formed a closed triangle. And so therefore you can deduce that that object is also in equilibrium. So what does this often look like from a kind of exam question perspective? Here's one. I've circled two things. We've got a ship pulled by two smaller tugboats. I've circled the idea of constant velocity. Constant velocity means no resultant force, no acceleration, so that is in equilibrium. Okay, not static equilibrium. Okay, it is moving, but it isn't accelerating. And that's the important bit. The other thing I've circled are the two angles. It's always worth looking at the angles that you're given. Are they significant or not? Add them up. 55 added to 35, 90 degrees. Brilliant. I'm going to form a right angled triangle. Okay, so what I've got to do is I've got to determine the resultant force and I know that this object or group of objects are in equilibrium, so I know that they should form a closed triangle when I draw each of the vectors. So to scale, I would draw a 2.14 kilonewton vector, and to scale tip to tail, I would draw the 1.50 kilonewtons. Okay, there is that right angle between the two of them. Okay, what I would then do is join them up, okay, and tip to tail form that closed triangle, which is the requirement for constant velocity, and I'd work out the resultant using Pythagoras. Okay, 2.14 square foot. I've not converted those into kilonewtons, but you get the idea. It's the hypotenuse of the triangle that I'm working out. Okay, so that's the graphical method. Now, it's a little bit time consuming. Sometimes you might have to do it, but it's one of the two ways of approaching this. As I said to you, more typically, you're going to be resolving vectors. So let's have a look at the example that you've got in front of you now. You've got a 120 Newton baby, and supporting that baby are two cables, each providing some tension. And if you remember a moment ago, I said I'd come back to the whole angle thing. The thing to notice here is you've got identical angles. That's telling you something. That's telling you that the two tensions are identical. Okay, because if they weren't identical, then the angles would not be the same. Now, we're going to consider life horizontally and vertically. This is very similar to what we saw a few moments ago. Okay, it's important to note where the angle is, first of all. Okay, so the triangle that I'm going to form is there, isn't it? That is my right angled triangle. Okay, and I've got T, that's opposite. So T cos 25, and presumably that is T sine 25. Okay, because that is the, no, it's not. Let's actually write that's actually correct. That's a bit embarrassing. Let's start again. That is opposite, so that is T sine 25. That is adjacent, so that's T cos 25. Okay, corrected myself. I must have the same components for the black tension vector as well. Okay, so if I consider things from a horizontal perspective, then we've got T sine 25 equaling T sine 25 from the blue cable. Okay, now I'm not considering weight because weight acts vertically. There is no component of weight horizontally, so that's all that I can say by considering things from a horizontal perspective. So what can I say from a vertical perspective? T cos 25 and T cos 25, they are the two vertical components of tension added together, must equal the weight. Okay, now I know what the weight is. It's 120 newtons. Okay, and so now I can work out the other aspects. I can work out the tension. Okay, by just doing a little bit of algebra. You've got the working out on that PowerPoint slide. Okay, you get a value of T to be 66 newtons. And you can check that and work that out for yourselves. Okay, so that's what it looks like when you've got two forces at the same angle forming right angled triangles. We've had a look at things graphically. We need to form a closed triangle. We've looked at things from a resolving vectors perspective. You look at things horizontally and you look at things vertically. Okay, what if the two angles are not equal to each other? Okay, so there's the example. You've got 55 degrees and 20 degrees as your two angles. Okay, I think you can see very clearly then that T1 and T2 are not going to be equal to each other. Okay, so what is your strategy here? Your strategy is still to form a closed triangle. However, it is not going to be a right-angled triangle. And this is where I just need to remind you a little bit about some GCSE knowledge that you've got around the sine rule. So the sine rule is how you work out sides and angles within a triangle that does not contain any right angles. And you've got the derivation for the sine rule in front of you. But the important bit is the outcome of it, okay, which you should be able to recall from your GCSE knowledge. Okay, so let's go back to the example that we've got then. We need to form that closed triangle. So we've got T1 and we've got T2 placed tip to tail, and we've got weight acting downwards. Okay, none of those angles are right angles. We've got the sine rule. So I guess we just need to kind of label what we mean by each of the sides. So I'm going to call that A, I'm going to call that B, and I'm going to call that C. And that means in terms of angle then, we need all three letters in each corner of the triangle, don't we? So we've got A, B, C there. So we've got A and B as our two sides, so that must be angle C. And we've got C and B there, so that must be angle A. So just kind of refamiliarise yourself with how we get to all of those angles. Okay, now if you look at the working out on the PowerPoint slide then, we now have to figure out all of those interior angles. Okay, so how do I know that angle A is 20 degrees? I know that because weight acts vertically. And if I look at the diagram, there is my vertical, there is T2, and there's 20 degrees between them. Okay, so that's how I know that angle is 20 degrees. And I'd like you to now work through the other angles and check that you agree with me as to their values. Okay, now getting to working out T1 and T2 then is just a little bit tedious, but we're going to apply the sine rule, and we're going to say that the sine, A over the sine of A is equal to B over the sine of B equal to C over the sine of C. Okay, and if you now have a look at the next line of working out on the PowerPoint slide, okay, side A is T1, angle A is 20 degrees. So T1 over the sine of 20 is equivalent to that first term that I've just circled. Okay, side B is T2 and angle B is 55 degrees. So that's equivalent to that term there. And side C is equal to the weight, and that's divided by sine 105 degrees. Okay, so in other words, T1 over sine 20 is equal to weight over the sine of 105 degrees. And because I know what the weight is, I can now solve and find out what T1 is. Okay, and if you work that through, you'll get 4,250 newtons. Similarly, T2 over the sine of 55 degrees is also equal to the sine of 105. Again, we know what the weight is. You can now solve that, and you can work out that T2 has a value of 10,200 newtons. All right, so you guys just need to go back to this and check that you are happy with that. Okay, having worked all of that out then, we now know weight T1 and T2. So I could draw a scale diagram, and if it forms a closed triangle, then I can deduce that that object is in equilibrium. Okay, I'm not going to do that, but you know how to do that. the more useful thing for me to go through is now the kind of the resolving bit of it. Okay, so on the PowerPoint slide then, I've drawn two right-angled triangles. Okay, one based on T1 and one based on T2. Okay, and I've split T1 and T2 into the vertical and the horizontal components. Okay, so there's T1, and I know that the angle with the vertical is 55 degrees. Okay, so I know that that is the adjacent side to the angle, so that's T1 cos 55, and that's T1 sine 55. Okay, similarly with the other triangle for tension 2. Okay, my strategy is always the same. Okay, I'm always going to resolve things horizontally and vertically. Okay, now remember weight is not relevant horizontally. Okay, so all I can do horizontally is say that the horizontal component of one of the forces is equal to the horizontal component of the other force. Okay, and that's as far as I can get. But the reason I'm going to do that stage is because I'm going to use it when I look at my vertical components. Okay, so vertically, the two vertical components add up to the weight. Okay, it's exactly what we did earlier with the baby example, isn't it? Okay, now I need to use both of those together. Okay, I can now take this expression here, okay, and I can say that T1 is T2 sine 20 over the sine of 55. So if I call that expression number 1, okay, and I can now substitute for T1. And then I can solve it, and I could work out T2. And then the second thing that I do is rearrange that first expression to say that T2 is T1 sine 55 over sine 20. And now I can substitute that in place of T2 to solve for T1. Okay, so that's quite a lot of information to throw at you, and I've not worked it all out for you. All right, so that's what I'd like you to do, and you've got all of the working out, obviously, in front of you. Okay, right, what now follows are just a couple of worked examples. Okay, so have a look at these. The first example looks at non-right angled triangles. That's really useful for you just to kind of get re-familiarized again with the sine rule. And then you've got some examples straight out of your textbook. Okay, again with the working out for all of those. And I think from this point forward, it's now about practice. So we've had a look at moments, we've had a look at torque, we've had a look at equilibrium. It's all about resolving forces and components of forces. You now just need a lot of practice on those. And that's where the past papers come in. And hopefully that's made some sense